All right, calculus people. As I had mentioned in class, I wanted to give you guys another example of a limit problem. It's a limit at a particular value of x, which is one of the two types that we're looking at right now in this chapter. The other being, of course, a limit as x approaches positive or negative infinity, which we refer to as end behavior limits. This one, though, again, is one of the three types that we have. Well, actually, it's sort of a hybrid of the three types that we have involved in this limits at particular values. The three types I talked about were simplifying complex fractions. I sometimes refer to as a common denominator because it's a big part of simplifying a complex fraction. When you have a fraction within a bigger fraction, it's called a complex fraction. So there's that technique. There is the multiply by the conjugate when you have a difference between a radical expression, like for example this radical expression and its subtraction. That's a difference of radical expression. So for that reason, this is kind of a hybrid of those two, where we're going to multiply by a conjugate at some time along the way through here, but we're also going to have to deal with the common denominator sort of situation. The third type, of course, is probably the most straightforward. That's just the factor and cancel. You get kind of a rational function, and you factor the top and the bottom and cancel out the thing that's causing 0 over 0. So for this one, there's a couple of different ways to approach it. I think the most straightforward way is to address the common denominator issue and simplify the complex fraction, and then deal with the conjugate part. But we can, maybe in this example I'll actually go through both techniques there. So the first thing we want to do is look for a common denominator. So in the numerator of the numerator, we have this factor of root of x plus 2 here and a 2 here. So this fraction is going to need a 2 in the denominator to look like this one, and this guy that has the 2 needs the root of x plus 2. So we're going to create that common denominator. I'll just write them as they are for right now. Root of x plus 2 in the denominator minus 1/2, and this guy, we'll give him a 2 in the denominator, 2 in the numerator, and this guy gets a root of x plus 2 in the denominator and a root of x plus 2 in the numerator. And that way we've established a common denominator up there, but again, this is still all over x minus 2. I don't know if I guess I probably blew off the most important thing about these limit problems. You always want to double check to make sure that direct substitution of your number, this particular value of x, direct substitution would give us 2 plus 2 is 4 here, the square root of 4 is 2. So we would have 1/2 minus 1/2, which is 0. Not necessarily a bad thing, but in the denominator we'd also have 2 minus 2, which is 0. So we'd get 0 over 0, an indeterminate form. So we have to do some algebraic hijinks to figure out what this limit is really, what this function is really going to approach as x gets close to 2. So back to our story here, we now have our numerator of our numerator would be 2 minus root of x plus 2. Let's see, x going to 2, 2 minus the root of x plus 2. And that's all over our common denominator of 2 times the root of x plus 2. And that's all over x minus 2. So it's at this stage that I think, again, we can go a couple of different ways with this, but I think it's probably most straightforward to deal with the conjugate issue right now. So we can take this guy and multiply by the conjugate of 2 minus root of x plus 2, which of course is 2 plus root of x plus 2 over itself to make it legal. And when we FOIL that out, we should get a result that's going to eventually lead us to being able to cancel some factor that's causing 0 over 0. Note that I only had to do that in the numerator, and again, that's because this quantity is essentially just 1. You can multiply anything by 1 and it doesn't change its value. So in FOILing this numerator out, we're going to get 2 times 2, which is 4, and then we multiply this negative radical expression by the positive radical expression, we get the opposite of that radical expression. So we get the opposite of x plus 2. And it's real important to include those parentheses right here. Again, this quantity root of x plus 2 and this quantity root of x plus 2, when you multiply them, where one of them is negative, you're going to get the opposite of that quantity, not just minus x plus 2. It's minus the quantity of x plus 2, because that's going to be a whole thing in a couple of minutes here as we proceed on. Our denominator is our original common denominator of 2 root of x plus 2, and then we've got this factor of 2 plus root of x plus 2 over there. So again, careful use of parentheses, 2 plus root of x plus 2. And right now that's looking pretty nasty, but trust me, it's all going to work out. So there's our expression right now, and all we're going to do at this point is simplify that numerator of the numerator and see what happens. So we've got 4 minus the quantity x plus 2. So that's going to be 4 minus x and minus 2. So that's going to be 4 minus 2, which is 2 minus x all over 2 root of x plus 2 multiplied by the quantity of 2 plus root of x plus 2. Fix that up a little bit. Now, that's all being divided by this factor of x minus 2 that's in the denom. So why don't we call that x minus 2 that's in the denom x minus 2 over 1, and realize that we're going to take that quantity and reciprocate it and multiply. So we're going to have 1 over x minus 2. And hopefully you're seeing right now that we've got some good stuff going on, because we have a factor of 2 minus x in the numerator and this factor of x minus 2 in the denominator. And that's going to give us the cancellation that we need, so we no longer have 0 over 0. So of course they're not quite the same as each other. One is 2 minus x and one is x minus 2. It is okay to cancel them though, as long as we find and account for that extra factor of negative 1, because 2 minus x is the opposite of x minus 2. So we'll put that negative in there and we should be good to go. That we have the cancellation, so the limit as x approaches 2 of negative 1 over 2 times root of x plus 2 times the quantity 2 plus root of x plus 2. And doing direct substitution now should save us from the 0 over 0. It looks like obviously our numerator is not going to be 0 anymore when we do our 2 in there. So we're going to get negative 1 over 2 root of 2 plus 2, so that's going to be root of 4, multiplied by 2 plus root of 2 plus 2, which is 4. So as long as we do our arithmetic correctly now, it looks like we're going to get negative 1 over 2 times 2 times 2 plus 2, which is 4. So let's see, that's 4 times 4, which is 16. So negative 1/16. And there's our solution. So what that tells you is this function, had we graphed that function right up there, written as it is, say on TI or on Good Grapher, and we looked at the y values as x got close to 2, we would have seen those y values getting arbitrarily close to negative 1/16. However, at the point x equals 2, we'd be looking at a hole in the graph there. Wouldn't even notice it on the graph, looking at it through TI or Good Grapher, but essentially there'd be a little tiny hole here at 2 comma negative 1/16 that graph would be just non-existent at. There would not be a y value there. So whatever the graph looks like, there'd be a little hole right there. Okay, so there's a technique. I think that's probably the safest way to go about a problem like this, and would certainly take you through any of what I would call these hybrid examples where we have a complex fraction, but it also includes a radical expression. Good luck.